Ready to start. Thank you very much to everyone for being here, and I deeply apologize for the delay. There were a lot of circumstances beyond my control that made us impossible to start on time. Let me start saying that the origin of this meeting, of this event, of this seminar, and also of this of the round table that will come afterwards. Do I sound more or less good, or is perhaps I don't even need it? I'm very genuine. Anyway, the main reason for being here together, united and reunited, is to give some sort of acknowledgement and the recognition of what I will say is a remarkable trajectory, teaching, researching, and educating young people in this faculty. And I'm talking about Professor Honorina Ruiz Estrada, which is here, and she is, in many senses, the reason of this event to be and to happen. We will explain that later in our roundtable, the reasons why we, not only me, believe that she was a key factor for the development of the scientific community in Mexico, working in soft matter physics, and especially in out-of-equilibrium physics. And before starting the seminar of Professor Dhont, I would like to ask to Dr. Gabriel Catu to come here with me and to Honorina, so we can give her an acknowledgement from the faculty for her 30 years of service in the faculty. I'm very sorry that Marta Palomino couldn't make it, and so we are doing on her name. And Honorina, as an academic son and as an admirer of your trajectory and of you as a person, and someone who is really grateful with what you did for me all these years, I'm very pleased to reunite your friends, your old students, and all these people that just as me appreciate very much what you did for us. Thank you very much, and you are an inspiration for many of us here. So.
On behalf of Professor Marta Palomino Banto, Head of the Faculty of Physical Mathematical Sciences, here to have acknowledgement for Professor Honorina Ruiz. We are very grateful and we are very happy to have you with us, and we appreciate all your hard work and excellent quality of not only your research, but also outreach and the preparation of human resources. Congratulations.
Pues muchas gracias a todos. Muchas gracias por estar aquí. Vielen Dank. Vielen Dank für euch. Hier Susanne, Gerda, Jan. Viel Zeit ist schon vorbei und wir treffen uns hier noch einmal. Mucho tiempo ha pasado desde que nos encontramos por primera vez en la Facultad de Constance. Me alegro mucho volver a verlos aquí. À la faculté de physique et mathématiques. Willkommen in Puebla. Willkommen an der Universidad Autónoma de Puebla. Muchas gracias a todos. Simplemente fue la bienvenida a nuestros queridos visitantes que nos acompañan desde muy lejos. Gracias.
So, before starting with our seminar, which is one of the main events today, I would like to just briefly comment, we will come to this point in the roundtable, that I'm very grateful also with Gerhard Megele and Jan Dhont, because they, as just Honorina said, they come from very far, from Germany, from Jülich, visiting and honoring this event in the name of Honorina. And I will sincerely thank for having the thought to come here and spend with us great time, and also to have discussions with the whole group in San Luis Potosí, León. Sadly, we couldn't have such an exciting meeting by yourselves. But anyway, we had the time yesterday to discuss a little bit other important things on our lives. So now we will start with our seminar, and I want to introduce to our honorable guest, Professor Dhont from the Forschungszentrum in Jülich. Professor Klein studied chemistry at the Utrecht Uni in the Netherlands. Sorry, I'm very nervous. Professor Klein studied chemistry at the Utrecht Uni in the Netherlands, and please correct me if I'm wrong, but during the beginning of the 80s, you studied your PhD in the Van Hoff lab with a genius peak. Is it well pronounced? A genius, please. Thank you very much. And then he worked as a postdoc in the University of Constance with Professor Rudolf Klein. Am I correct? And then Professor Dhont worked as an associate professor of physical chemistry in the group of Henk Lekkerkerke. And then in 2000, the year of 2000, he became professor in Düsseldorf. If I'm in this, how it is called, this Jülich?
So the Jülich model, it's called.
Jülich model.
Professor at the university, but your work is actually
in the Forschungszentrum. Okay, that happened in 2000, right? And from that time, he works there, and he's visiting us today to present a talk with the title Motility-induced interparticle correlations and mass transport. Jan, thank you very much for your visit and this seminar.
Thank you very much. Let me first say that it's a big honor to be invited to give this talk on the occasion of the in honor of Honorina. So I will talk about motility-induced interparticle correlations and mass transport. So I will explain, of course, what this all means. But let me first show you two photos from 30 years ago, where I met with Honorina for the first time. So here you see, this is Honorina, which is clearly recognized also by you already know her from this time on. This is me. You might not recognize me. And this guy you will probably not recognize at all. He is sitting here in front. But I don't want to. And this is so Magdaleno. So he's not here, so we cannot offend him.
No, we can just say it for him. Can we go back to this picture where he's
And this is Honorina from the back, so you won't recognize him. And as you of course also mentioned Olegario, I had Sugaret and I had a lot of contact with him and we still have. So he's something that in the back. Olegario wise. So almost every talk about active systems starts with a movie about swarms of birds. But of course this is PDF file because my computer did not work, so I can't show you the movie. But these birds swarm around and you probably saw that for yourself at some point. So what is this stuff? Anyway. So to explain this, people made videos of these birds and checked their position as a function of time. And it turns out that birds that fly at the edge of the swarm tend to fly inwards to protect themselves against the predators that fly around this swarm. And that of course stabilizes the swarm, so it keeps the swarm intact. So birds at the end want to go inside to protect themselves. There is no leader, so the change of direction of this collective motion does not depend on a single bird, but it is at random. And it is due to the correlations between the interactions between these birds. So these videos show that each bird interacts with about 7 neighbors, and it adjusts its flying direction according to the average direction of the flying surrounding birds.
The number 7 comes from the analysis of the videos?
Yes.
Ah, okay. It's the average number of neighbors in all the videos. Okay.
So these videos are used to identify the correlations, the interactions between these birds. Now, of course, colloidal particles that propel themselves, or bacteria, also interact with each other, but of course they don't have a brain to say, I'm now going to adjust to the velocity of my neighbors. So these correlations have a completely different origin, and I will discuss the origin of these kinds of correlations. So we're going to talk about motile particles, which are particles that act with a force onto the surrounding fluid and thereby propel themselves. So these are called motile particles or active particles. So these are two examples. So bacteria do this. For example, this is so well-known bacteria that actually the force by these flagella, so they make a breaststroke motion, which they pull themselves through the fluid. And this is an inorganic active particle. So simply one example, there are many examples of this, where you have a Jadis particle. So you have a silicium oxide core, which is coated on one side with gold. And the fluid in which this particle is embedded contains peroxide, so H2O2. And gold so catalyzes the decomposition of peroxide in water and oxygen. So you convert two molecules into 3 molecules at the site where you have the gold. And that means that the number of molecules on the gold side becomes larger than the number of molecules on the oxide, silicium oxide side. And that will exert an additional pressure on the gold. So that pushes the particle through the fluid. Yeah? I hope that is clear. So these are just 2 examples of active particles or motile particles. Now at a higher concentration, these things start to interact with each other. And that of course will affect the phase behavior of these things, it will affect the mass transport, etc. So the simplest model system that is available to investigate these kinds, so the phase behavior and mass transport for these interacting particles, the simplest model are so-called active Brownian particles. So this is first of all, by definition, what you call an ABP, an active Brownian particle. There are no hydrodynamic interactions. So hydrodynamic interactions are due to the fact that one particle moves through the fluid. It induces a fluid flow, which of course affects other particles in their motion. And these so-called hydrodynamic interactions in this very simple model will not be considered. So we consider only direct interactions between these particles. The swimming direction is quantified by a unit vector, u, along which it will swim if it does not interact with other particles with a velocity v0. So we have a rotational Brownian motion on top of translational Brownian motion, which changes the direction of this unit vector, and thereby it changes the direction of swimming. And this velocity v0 will be a constant independent of the direction of swimming. But of course it will change due to interactions with other particles. Furthermore, we only consider exclusive volume interactions between these spheres. That is to say, they don't interact when they don't touch, and as soon as they touch and the cores try to interpenetrate, the potential goes to infinity. So these are called exclusive volume or hardcore interactions. So this is the simplest model that you can use to be able to describe what these active particles do at higher concentration. So you could, in principle, if you could solve equations of motion that we are going to define in a minute, you could describe the phase behavior due to interacting motile particles. You could describe the effect of activity of motility on the dynamics. You could determine the rheological behaviors or the flow behavior of these systems, etc. So we are going to do a microscope theory for these systems on the basis of what people call the Smoluchowski equation. Now, this is an equation of motion for this probability density function for n of these particles, for the position coordinates of these particles and the orientations of them. And so there are three terms. So the first term is due to translational motion. So if you're familiar with Fick's law, you see here the diffusion coefficient on Laplace Pn. It is so Fick's law, if you like. So do you know Fick's law? You ever heard hear of Fick's law? So who is not familiar with Fick's law? Who is familiar with Fick's law? So many people are not, or so many people are both. Anyway, so this will be the only term for non-interacting passive systems, which is called Fick's law, which goes back to 1850. And then there is a force on the particle due to the interactions between them. So this force is the gradient of the position coordinate of particle J, working on the total potential energy of an assembly of n of these particles. So this would be minus the force on the particle due to interactions between them. And then there is a rotational contribution, which changes the direction of this unit vector u. And that is proportional to, so the time derivative of this PDF, this probability density function, is equal to the so-called rotational diffusion coefficient. And this is the translational diffusion coefficient. And this is the rotation operator, which is the outer product of this u gradient u, which you might remember from quantum mechanics about angular momentum operators. This is proportional to that angular momentum operator. And this is all for passive systems, but now there is an extra term due to the propulsion. So this is equal to a probability, the divergence of a probability flux, which is of course equal to Pn, and then this velocity in the direction of J. Okay, so this is the basic equation that is actually well known, on the basis of which I will try to calculate some correlation functions and mass score for interacting active particles. Now what you're interested in then is this object, which is the density, the number density of these particles at a point r with a specified orientation u. So this is a kind of concentration, a number of particles per unit volume, but only those which have a specific orientation u. So, and that is proportional to the probability to find a single particle at point r with orientation u at time t. And you can get that from the integration of this Pn over all coordinates except for particle 1 say, which then has position r and orientation u. So you integrate the Smoluchowski equation on both sides, and you obtain an equation of motion for this orientational density. And that looks like this. So here you have three translational diffusion for non-interacting particles, passive particles. That is this term. So this that can be Fick's law, 1850. This is the rotational contribution to the change of this orientational density. Also again for a freely non-interacting particle. And then you have this extra flux, which is due to the self-propulsion. But then the important term is this one. So this is the effect of interactions between the particles on this time derivative. And it's an integral over a so-called pair correlation function. I will explain what this is. This pair correlation function is the central quantity. If you know this pair correlation function, how it depends on how our prime is moving down, you know everything. You can calculate phase behavior, dynamics, etc. Now what I'm interested in are these density variations, which are smoothed on the length scale of the range of the pair interaction potential. So I'm going to consider density variations, so this is the density as a function of position. I'm going to be interested in density variations with a long wavelength, much longer than the range RV of this interaction potential. So I need only here distances which are close together such that this thing is non-zero. So the gradient of V is zero beyond distances of the order of the range of this potential by definition. So I need only the short range behavior of this UR. But of course, short range behavior relaxes fast in comparison to the long ranged concentration variations. So you might say this GOR relaxes almost instantaneously to the local density. And you might call this the statistical analogon of local equilibrium. So locally the G takes its equilibrium form, or in this case rather its stationary form, at the local density. Okay, so what is this GOR? So it's defined as follows. So this is a this P2 is a two-particle probability density function, and let's talk about passive systems first, where you just have the positions of two coordinates without these orientations. And if there are no interactions between particles, this thing factorizes in two P1s with the probability to find a particle at some position. When they don't interact, you have a factorization. If they do interact, this is no longer valid. You have to correct this with a vector, with a quantity that is called the pair correlation function. And this thing then characterizes how particles interact with each other. For passive particles, it is known that this GOR, pair correlation function. So for low concentrations where binary interactions are dominant, that is simply the Boltzmann exponent of the pair potential. So that is simple, that is well known. For motile particles, this is no longer true. And the question is, what is this GOR for low concentrations with activity? And in fact, there's a whole industry of papers which try to calculate this GOR at higher concentration via Ornstein's unique approaches, which I will talk about a little bit later. But for some motile particles, there's absolutely nothing, not even on the pair level, not even at low concentration. And the reason for this is that the calculation of this thing is not so simple, I guess. So we're going to talk about interactions between just two particles, which can have a different orientation, and try to calculate this GOR for these binary interactions, so at low concentrations. Now you can also get the equation of motion for this pair correlation function by integrating this Minkowski equation over all coordinates except for two particles in this case. So you get a P2. And then you put this time derivative equal to 0, because we are interested in the short range behavior, so the stationary form at the local concentration. and you can dimensionalize this, so the resulting stationary equation for this GUR. So, for example, instead of the distance between two particles, we take the distance between the distance that they should have so at contact. So this is 2 times the radius of the sphere. So this not linear is the dimensionless R. So this has no dimension anymore. And what you see here, so here's again, you could say, so fixed law, the Laplace of G. Here you have the rotational contributions, which changes the swimming direction. And this term now accounts for the activity of the particles. So this U is the difference in orientation between the two particles, which is proportional to the relative velocity of the two particles. So if the orientations would be equal, they would move alongside. Right?
Excuse me, I have a question. So the particles can move at different velocities? I thought that they all had the same.
So the magnitude of the velocity is fixed, but the direction of the velocity
It's different.
so changes with this vector u.
Oh, I get it.
So and it changes due to rotational boundary motion. Yeah. So the magnitude is fixed to this v naught.
Is this difference defined in a different space as the one of the R vector? In the sense that these vectors are unitary vectors in a unitary sphere, right?
Yes.
So the difference, where does it live? Also in the unitary sphere or tangential to the unitary sphere?
So, let me see. Here. For example, I have two particles with different positions, of course, and one can move in this direction at some point, and the other one can move in another direction.
Okay, it's just the difference of two vectors in the Euclidean space.
Yeah.
Okay.
So if this U1 is parallel to U2, so they just move along to each other.
Okay.
Yeah, and this relative velocity is multiplied, and that is the important parameter, is this lambda, and this lambda is called the swimming peak-length number. And it's defined as the ratio of the radius of the particle multiplied by this fixed v naught, the velocity of a single non-interacting sphere, and the translational diffusion coefficient. So it measures the importance of displacement due to swimming and relative to the displacement due to Brownian motion. So if this lambda is large, displacements due to swimming are much more important than displacements due to Brownian motion. So lambda is large for a large velocity, lambda is small when Brownian so diffusion is more important, so swimming is small. Okay, and then you have, of course, two boundary conditions. The one is that these cores cannot interpenetrate, so the flux, when two particles approach, they cannot interpenetrate. And this is, so this equation, so when they touch, they cannot interpenetrate. And of course, there are no correlations when the distance between particles becomes large. So the G should become equal to unity, so the P2 will factorize if the distance becomes very large. Now, the question is, what are the important variables? So here is the distance, this big line is the distance between the position coordinates between particle 1 and 2, say. Particle 1 has an orientation U1, particle 2 an orientation U2, and the difference between them is this big U. Now you would maybe expect a cylindrical symmetry about the relative swimming velocity. So the variables then are the magnitude of the distance between them, the magnitude of this u, and the vector theta between these two vectors u and r. So I'm going to work with cylindrical coordinates, where the z direction is this u, so the relative velocity of the two. So I'm going to introduce this rho, the cylindrical coordinate, that is the distance between this line, between the z-axis if you like. And of course the z is the distance of this r along the u direction, the big U. So these are the three variables, so z, rho and r. Now suppose that the z is negative. It is easy to see that particle 1 moves away from this particle 2. So for z is positive. So when z is positive, this particle moves away from this particle. And I will call that the wake sector. So you now have to make a distinction whether the particles move apart or they approach each other. So the front sector, the z is negative. So then particle 1 will approach particle 2, and at some point they will start to interact. So the front sector and the wake sector. Now let's first see what happens as small peak numbers. So diffusion is still very important, and swimming has a little effect. So pictures are now missing. But there should be a picture here, which is not there. So for small lambda, you can simply do a linear expansion with respect to lambda. And you can solve these equations and you find this expression for g of r. Now it is essential that I would have been able to explain this picture, but how I have to look at formula. So here you see the z, so the cosine theta. So if this is so positive, then you are in the front sector where the particles approach each other. And then you see that the g of r is larger than it would have been without interactions. So the g of r without interactions is 1. When this cosine is positive, it is smaller than 1. So you're actually in the wake sector. And it's unfortunately that I don't have this picture. So when two particles approach and they hit each other, the probability will be larger than 1. If they surpass each other, so they move away from each other, the probability will be smaller than 1. So you have an accumulation of probability when they hit, and you have a depletion of probability when they move apart. And I will explain a little bit later why that is. So now large big numbers, it is much more difficult. So we go to large lambda. And so this is the equation of motion where I divided everything by lambda, because 1 over lambda is not a small number. Now you could say, well, 1 over lambda is small, so I'm going to neglect this term. And then you end up with this equation of motion, which is of course because this is also small, right? So you end up with the divergence of u times g is 0. Well, that is a first order differential equation, but you have two boundary conditions. And you cannot use, solve a first order differential equation and fit two boundary conditions to it. So this means that this term here is not small. You have to keep this term. And that so implies that the gradients, spatial gradients of the g of r are very, very large. But they can also only be large in a small region. Right? And that small region is called the boundary layer. So we have a small region where gradients are extremely large. So this is called the singular perturbed differential equation. You cannot expand it, so in a power series with respect to this one lambda, the small parameter. So what you then do, in the so-called boundary layer analysis, you blow up this region, this boundary layer, such that this term becomes equally large as that term. So as this term, so that this is order 1. So you introduce a new spatial variable, this S, which is lambda times r minus 1. And you rewrite this equation of motion in terms of this S. So this is the gradient operator with respect to this new variable S, so this boundary layer variable S. And then you find this equation. So this is equally important as U. And now you neglect this, you have this simple equation that you have to solve. And what you find is, so particle 1 comes from below. So this is particle 1, so this is particle 2. Particle 1 hits particle 2, so when they are in contact, they cannot interpenetrate. So there is a small region where the probability is very large. So this G is proportional to lambda. And the width of this region is very small. So gradients can only be larger within the small region. So you have a small region with a very high probability to find a particle being in touch in the front sector. And this is the solution of that relatively simple equation. And you see here that when r is a little bit larger than 1, so they're almost in contact, due to this large lambda, this will give you 0, so you should go only a little bit away from contact to find the g of r that is equal to 0, so equal to 1.
Yes, one question.
Yeah.
Does the product of lambda with the difference of the orientations represent physically something? The meaning of lambda times u?
Well, this is, you could say the lambda u, that is the dimensionless form of the relative swimming velocity. So if you go back to this here, lambda here. So if you replace this v0 by the real velocity, so the v0 multiplied by u1 minus u2, then you get the lambda big U. Then this lambda is the ratio of that velocity with these two orientations with respect to d0. So this is just the magnitude of a single sphere. When you multiply this by this big U, you get the relative velocity of the two. And that you dimensionalize with respect to d0.
This was the measurement of how much is the let's say, activity against the Brownian diffusion, right? But then times the difference of it is related to this probability of collision. I mean, given that you have the orientations, you know whether they are going to collide or not, or represent something like that.
It's a given probability. So it's probability for a given distance and to given to you. So you only I mean, you find so it's a function between the separation of the two particles and at the same time of the two orientations of the two particles. Okay, so now we go to the wake sector. So particle 1 approaches particle 2. So here in the front sector, and then it moves away. So it passes particle 2. And this probability to find a particle here, the finite probability is entirely due to diffusion of this particle into this region. Right? So it passes particle 2 here, but then it has to diffuse into that region to reach a finite probability to find that particle somewhere. So there is, if this velocity is large, then of course there will be a large region, the wake, where the probability to find the so the color of particles is small. So you can do a simple scaling simulation to assert the extent of this wave. So this angle over which, so suppose L is the extent of this wave. So at distance L here, the G of R recovered to unity. And then, so it has to move over an angle here, which is equal to this delta theta, which is equal to the radius, proportional to the radius divided by the extent of this wave. Now, if you consider only a rotational motion, the time it will take to turn over an angle delta theta is equal to delta theta squared divided by the rotational diffusion coefficient. But on the other hand, L is of course also proportional to the velocity multiplied by the time that it so will take to reach the end of the wave. If you put this all together, you find that the length of the wave in terms of the radius of the sphere scales like the big number to the power 1/3. Now you can solve this the equation in the wave. You will get this complicated equation where you have here two Bessel functions, and you see this 1/3 length of the wave over here. So you have the distance to the power 3 divided by lambda. So that tells you that the length of the wave scales like lambda to the power 1/3. And you can see this in the picture. So if you plot this thing as a function of g and rho, so you find this wave. So the probability here is small, and here is 1. So you have a very anisotropic DUR, which is very large in the front sector, and only different from one in a very small region, so this boundary layer. And here is the opposite. The G of R is essentially equal to 0 here, because there is no time to diffuse for the particle into that region. And you have a very smooth transition to G code to 1. So a very high G, only a small region, very small G in a large region.
There is no hydrodynamics.
No, there is no hydrodynamics here. So for these ABPs, these active bound particles as a model system, they need direct hydrodynamics. The question is how important it is. Okay, now we know this G of R. We can go back to this equation of motion of the density. So we now know this thing, at least for low concentrations. And you can calculate this entire integral. To get an equation for the volume fractions, so the fraction of the volume that is occupied by the cores of the colloids. And that is of course an integral over the volume fraction of the colloids at point R with an orientation u. So this integral integrates over all orientations of the particles. And then you are just left with the concentration, the volume fraction of all the colloids at the point R, irrespective of their orientation. And what is also important is the so-called polarization. So that is the preferred direction that interacting spheres will take. So that if this P of R, the polarization is pointing is so non-zero, pointing in a certain direction, that will be a preferred direction of two particles which interact with each other. So now if you calculate all this, so you integrate over this u of all u's, and you evaluate also this integral, because we know what this u bar is, for large lambda. You get this equation, where this is independent of this polarization. And here's the polarization. So you have to calculate the polarization as well. So what you do is you multiply this by u, and then you integrate. Then you get an equation of motion for this polarization, which is equal to this thing. So here's the polarization, here's the gradient and the density. And then I put this equal to 0, and it is called enslavement. So this term is very large in comparison to this term for small gradients in the density. And then you can show that the polarization is enslaved. It adjusts instantaneously to the local concentration or the local gradient in concentration. So you put this equal to 0, that is called enslavement, and you get this expression for P, you put it in here, and you get a closed equation for the concentration. And that is this equation, so it is almost a fixed law, except that this diffusion coefficient is depending on the swimming velocity. And for large lambda, the normal fixed contribution can be neglected, so this lambda is very large. And you see that mass transport is dominated by the motility of these particles. Now important is also that this P is directed from high to low concentration. So particles attain a preferred orientation that goes from high concentration to low concentration. And that of course gives a contribution to the d phi of t that increases the rate of homogenization. So if you have an initial gradient concentration, swimming, the effect of swimming is that it relaxes to the homogeneous state much faster as compared to passive particles. So, and this means that some motility actually counteracts the spinodal decomposition. So what is spinodal decomposition? That is a thermodynamically unstable system, and then we explain also the origin, which is well known to the students, I hope. So suppose the concentration is a function of position. You make a photo of the system and you have a certain fluctuation in the density. So this is the, let's say, this is the instantaneous concentration as a function of position. That is fluctuating quantity. So this is a snapshot. Now we're going to look at the force on the brine particle in this gradient. Now suppose that the interaction potential between these particles is attractive. Since there are more particles here than here, the interactions will pull this particle to regions of higher concentration. Now of course there is also a force in the other direction, this is called the Brownian force. But if the interaction strength is large enough, the effective force will pull this particle to higher concentration. And that is the initial stage of phase separation. So inhomogeneities will increase. Now we just saw that some motility goes, the so preferred orientation of particles is from high to low concentration. So what happens, so this is what Kahn and Hilliard in the theory for spinodal decomposition called uphill diffusion. So you have a net force in this direction. But now for multicolloids, you have a flux in the opposite direction because you had preferred orientation from high to low concentration. So you have a flux in this direction. And if this plus that is positive, so it goes from large to low concentration, then you will not have spinodal decomposition. So motility inhibits spinodal decomposition.
I have a question. But do you also assume that you have a attractive interaction potential?
That is a good question. That is not in the theory. So it would be nice to extend So I only consider hardcore interactions, so without attractions.
But then how can occur the instability?
Yes.
No,
that's
but
right.
I think that the principal thing that you have this preferred orientation, you will have to probably also for attractive spheres. Yeah, but to be sure about that, you have to repeat the entire theory for attractive spheres. So you're right that this depends on my guess that also for attractive particles you will have a preferred alignment from high to low concentration. But my intuition tells me that it will not change if you have attractions. Is that an answer to the question?
Okay.
If not, we can talk after.
Yes.
Probably what you say is that it's not only spontaneous fluctuations, but also you can cause it on purpose. And then Fick's law will say that the tendency to restoration in in spinal decomposition that amplifies.
Yeah. So the effective diffusion coefficient becomes negative. You get uphill diffusion.
And what you want to say is that activity counterbalance is a counter effect.
Because they tend to move, so they tend to attain an orientation that is from high to low concentration. So it transports particles from high to low concentration instead of uphill. So let me give a summary and outlook. So you have so at large peak numbers, you have an extremely anisotropic GFR. You have a large contact value, so where they touch each other, that diverges like lambda, and the spatial extent of that boundary layer is very small, it varies like 1 to lambda. And on the other side, in the wake, you have exactly the opposite. You have a GFR that is essentially equal to 0 when they touch, and it is a very extended region that varies like lambda to the 1/3. So it's very, very anisotropic. So concentration gradients, so that gives rise to a preferred orientation of the spheres, which then tend to go from high to low concentration. It inhibits spinal decomposition. And now for the future, what you would like to do is maybe add other types of interaction potentials, like also attractive potentials. You would like to include hydrodynamic interactions. And you would like to extend this to higher concentration. And I think there are 2 ways to maybe do this. You can apply a closure relation that does not, so in an Orstein-Zöllning approach, that does not require the specification of a potential. Which you simply take the C equal to this G0 that you just calculated for 2 particles. The direct relation function being equal to this G0 and -1 for distances where they don't touch, and you don't know what they are inside, and you know that the total correlation function is -1. That could be one route. The other route is to map this on a passive system with a potential that is equal to -kBt log G0. So you take a passive system with an interaction potential that is this thing, and then do the normal Orstein-Zöllning for passive systems. And this is a kind of anisotropic so-called SALR system, where you have a small raised attraction on one side in this case, and a long-range LR potential on the other side. So this would be an interaction potential that is highly attractive on this side, and long-range so repulsive on this side. But I'm not sure how accurate that map would be.
So in this mapping, one should have in mind like situations in which I have two orientations which push the particles together, and this is the source of my attraction in the solid potential. But what should I integrate then in orientations of the group?
Of course, so in the orthogonal equation, you also have integrals over U1 and U2.
But those are constantly changing by means of
Then you have to integrate that to get correlation measures. So normally you have this integral of dr prime, h, r minus r prime, c r prime. Now you have to add integrals of du1 and du2 with the du1 prime and the du and so and the u prime, so u2 prime. So you have to add these integrals of orientation to the orthogonal equation, which is of course difficult. So maybe possible. And that's what I would like to think.
Thank you very much. Questions from the audience? No? Magdalena?
Yeah. I didn't figure out. This is let's say a low density limit of the theory, or is for arbitrary?
This is for low density, so this is the analog of swingers for this formula for passive systems. So for first order concentration, for low concentrations, where you have some binary interactions predominant, then this is the GUAP for passive systems. And what I talked about now is the equivalent of this thing, but now for active systems.
Okay. And do you have you thought about how to go to higher concentrations with?
Well, so one way, or the most important way to do that is to Einstein's early.
This one?
Einstein's early. So you know Einstein's early theory?
You mean for the pair correlation function? Yeah. And okay. That would be a beautiful project.
It was very difficult.
Okay.
And the definition of this UR is the same. The definition, if you were to calculate G, you will calculate the same way that you calculate G of R in a given system.
Yeah.
The number of particles away from center mass.
And of course, it depends on two orientations as well.
Right. But it's the same.
It's the same thing.
I have a question. Is this visualizing a 3D space or on a plane?
So this is in 3D.
But I got confused because when you were talking about the cylindrical coordinates, I thought you were thinking on a plane.
No, this is cylindrically symmetric, so around this U.
Oh, okay.
So it's independent of third angle, so that goes like this.
Okay.
Any other question from the audience? Okay, if not, please, we thank again Professor Dhont. This is a small gift from Honorina and Patricia Mendoza. For your kind contribution. And we are now having a small coffee break until we organize the round table, so feel free to just have a coffee and relax.